Right. Good morning, everyone. I hope you can hear me. I'm looking at the chat, so if someone would type yes, they can hear me, that'd be great. Right, great. Okay, you can stop now. That's fine. Okay, so I hope you can see this. We're recording this session, just to let you know. Right. Okay. So welcome to ELEC1207. My name's Nick Harris, and I'm the module lead for this module. This recording system. So without further ado, then we'll get straight in, and I'll tell you about the makeup of this course. You've already had, or should have had, Paul Lewin already yesterday, so maybe he gave you some introduction to this. But there are four main strands to this course: circuit theory and analysis, and basic devices, which are transistors and op-amps mainly, and then how to apply the circuit theory that we've just learned in the preceding part, in this bit here, how we can apply that to start to make some circuits. Then Professor Maunder will be talking about communication techniques, which is basically more complex ideas that can be implemented with these basic devices, transistors and op-amps that we've learned about from me. And Paul will be teaching you about control theory, which is another way of using the basic devices to do things that you actually want. And controlling of things is a really important subject, and Paul is a really good person to lecture that. Right, I'm going to go full screen now, I think. Right, so if you've got any questions, put them in the chat and I'll see if I can answer them as I go along. Depends how many there are. If there are too many, I won't be able to do that in the time available. Right, so there's notionally 4 slots a week. Normally these will be 3 lectures and an associated, but effectively now we've turned them into 4 lectures, as you probably realised. No difference between those slots. Basically, we're running parallel. You've got 2 slots with me, 1 with Paul Lewin, and 1 with Rob Maunder in the week. And this is what the timetable looks like as of yesterday. It's still in a state of flux, so it might actually move around a bit, but just keep an eye on it. So this is where we are now. Obviously, you get me again tomorrow at 9 o'clock, which is a bit. There's lots of 9 o'clocks actually, and then you get Rob at 9 o'clock on Thursday. So it's 9 o'clock starts for everyone, but at least that gets the day off to a flying start there. Assessment. Well, what can I say about assessment? This year, we don't know is the answer at the moment. On a normal year, and it won't be too dissimilar, I expect, that we have an exam, we have some coursework, and we have some lab sessions associated with this. Now, lab sessions have been cut down a bit. We're hoping to get lab sessions up and running after Easter, and we will be running 2 out of 3. That's the intention, is to run 2 out of 3 of the labs for this course to give you a good flavour of what's going on. If you're really keen, you can look up the other lab. You might be pleased to know that the lab you're not doing at the moment anyway is the transistor design lab, because that is a bit fiddly and a bit frustrating if you don't have a lot of attention to detail. The other 2 labs, which is op-amp lab and some communications lab using MATLAB, they can go ahead and they should be okay, but they're equally awkward as well in my mind. And each lecturer, so that'll be 3 pieces of coursework. Deadlines will be out in due course. I'm still deciding exactly how we're going to run this, but I'm thinking that what we will do is have it online. So you do your coursework, do it on a piece of paper, write it all down, all the answers, and you're working. That's really important. Working is really important. And then enter your answers into a quiz on Blackboard. And you will have a short amount of time to enter your answers into the quiz, which means you can't do the coursework while you're doing the quiz. You must have done the coursework beforehand. So really just copying your numerical answers into the quiz, submit that, and then when they're all in, it'll get marked automatically. But you would also need to submit your written answers into the hand-in system in case anybody wishes to appeal or argue with the answers. And we'll have some evidence that you can imagine there's 160, 170 of you on a good day. only 58 at the moment, I note. That's an awful lot of marking to do when it's online. So we'll try, I'll look into that and see how it goes, but you'll be informed. I'll keep you updated as to how that happens. So feedback from last year. I say this, in the main, people enjoyed the course, which means that not many people complained. It is undoubtedly a hard course. Yeah, there's a lot in it. It's got lots of proper engineering in it. There's sums, there's theory, there's abstract ideas, and there's quite a lot of it, from basic devices all the way up to full systems. So there's a steep learning curve on this. So don't get behind, and that would be my absolute top tip. Do not get behind. I'm going to try and put a few little quizzes as we go up on Blackboard as well, so that you can just quickly get a little bit of revision on what's happening in the lectures. Right, it does require a good understanding of Professor White and Dan Spence's course from semester 1. That's going to fill some of you with some horror, I'm sure. Do not get behind. And as always, there's some changes. This year, there have been a few more changes to try and make it, well, I say easier, to try and make it smoother for you to assimilate all this information. But all this material that you're being taught here is important for later years. Some of it will be gone over again next year as sort of revision because it's so important, but it's important that you get a handle on it this time round. There's a few books. Basically, any general electronics textbook will be absolutely fine. We're not doing anything that's out of the ordinary here. It's basic electronics and communications. You can find it in almost any book. There's lots of resources online for other methods for explaining it. There are some other, you might find other lectures online as well on YouTube, things like that. I've been looking at a few of those. Some of them are very good, some of them not so good, and some of them are plain wrong. So just be a bit careful on your sources if you're looking at it elsewhere. This one's a good book. I think it's out of print, but there's lots of electronic copies in the library which you can have a look at. It's a very big, fat, thick book. It'll cover all of your electronics and more for the next few years. This one is smaller and easier to enter and is a little bit more basic, but is probably it's a good book actually. And again, I think there's some electronic copies of that one in the library as well. But we don't teach from the textbook. It's not necessary to have a textbook. You don't need to rush out and try and buy one or anything. I've got very comprehensive notes, as you'll find out as we go along, that should help you. There's lots of examples in there as well. It's basic idea, and there are loads and loads of sources of this information all over the place. Right, so circuit theory. So in this section, we're going to be looking at linear circuit theory, and it's important that we understand what linear is, and we'll worry about the definition of that shortly. So what we're going to do in this chunk of work, which will be a few lectures, so don't worry, we're not going to do all this in one lecture. We're going to do some definitions. We're going to look at the basic circuit theorems, which include nodal analysis, mesh analysis, and superposition. These are the three: superposition, mesh, and nodal, which will be the mainstay of any circuit analysis that you do going forward. These basic techniques then lead us on to some interesting theorems, and in theorems in this case means shortcuts. So we end up with looking at something called a Norton and Thevenin theorem, which Dan may have touched upon as he's gone forward. And then we have things like ladder networks and star pi transforms. Dependent sources, probably not immediately apparent what they are at the moment, but they're quite important. They're very important because they're basically ways to analyze transistors. They're a bit of a special case, and we'll look at those as well. You will find SPICE a useful tool, and I'm not talking about the drug. I'm talking about the circuit simulation tool. So SPICE is a circuit simulator. You may or may not have used circuit simulators. By the end of this course, you will have. There are many different versions of this program called SPICE, and we'll talk a little bit about SPICE later on in the course about why it's called that and its history and everything. But at the moment, I would suggest that there's a good free one, which will be really, really useful as you go forward, available from a company called Linear Technology, who make a lot of chips going forward. and it's called LT Spice, and LT stands for Linear Technology Spice. So it's just their version of this circuit analysis package. You can get it from here. You can search online for LT Spice, download it. It's free. There is a version for Mac. It's not quite as good. So you might want to run Windows in a virtual environment if you're running a Mac. And there are other Spice type systems available on departmental computers such as OrCAD or Cadence or Multisim. There are loads of them. Doesn't matter, they should all give you the same answer, but I'll be using LT Spice as we go forward. Okay, so the first section that we're going to talk about are definitions. So it's a bit boring, but we need to get them out of the way because we need to understand what we're talking about. Definitions become really important for analyzing circuits. There's no space for approximate answers and guessing what's going on. So we just need to run through some of these. Hopefully they're revision, but it's, as I say, it's important that you do get this. So circuit theory notation. We've got various definitions of bits and bobs. So we've got a circuit element, which is a mathematical model of a practical device or component. For example, a resistor. A resistor is a circuit element, capacitor, inductor, that kind of thing. And an electronic circuit is an electronic network containing a closed path. So it's got a loop, and we'll look at some of those in a minute. And we have something called a node. And a node, we'll be talking a lot about nodes. We've already discussed nodal analysis briefly. It's an interconnection point of two or more ideal circuit elements, elements being resistors, capacitors, whatever. So it's two things joined together. So the connection point of two resistors. And we'll have a look at trying to spot these in a minute. And then a branch is a circuit element plus two nodes. Okay, so that's an element with two wires hanging off it. And then a mesh or a loop is all these things come together to make a closed path in a circuit. Right, so there's lots of words, all very boring. What we need to do is have a look at a picture. So here's a picture of a circuit schematic with various different devices in it. So just to be sure, this is a voltage source. There are various different symbols, but this is the sort of symbol that we're going to be using for a voltage source. Plus and minus tells us which way around it's driving it, and the value, 2 volts. Here is an element. It's a resistor, and here's another one, labeled element. There we go. Element. We've got another element here. A source is also an element. Okay, so all these blobs are elements. We've got a node. A node is where two elements join together, or two or more elements join together. So here's a node. It's easy to spot. It's a junction. Yeah, 3 of these elements are joined together to make a node. This one's not so obvious. There is a join here. 2 elements are joined together, and this is a node. It's a node of only 2. This one's a node. Hopefully, it's got a corner drawn into it. It's a node. It's the same as this one. We can make this one cornered if we wanted to. Okay, so there's a node. A branch, an element, and 2 wires. Yeah, that's all we're talking about there. And then we've got a mesh current. So this is a mesh around here. It's a loop. Yeah, and this is what we will call the mesh current going around here. So there's 2 meshes here, one going around this loop, one going around in this loop. So all those words that we saw earlier are actually quite straightforward when it comes down to it. We're just talking about bits of a circuit. So basic revision of the ideal resistor. We're going to be doing a lot of work with resistors in this part. So resistor is a circuit element, okay, which is used to define energy dissipation in a circuit. So we're starting to get a bit abstract. That's what it does. It just gets rid of energy. Capacitors and inductors do not get rid of energy. They store energy in different ways, but that's what they do. Resistance, which is where its name comes from, directly opposes current flow, and the energy dissipated appears as heat. It's officially the only way of getting rid of energy in a circuit. You turn it into heat. Even LEDs and things are effectively like resistors. They turn it into light, which is a form of heat. But the relationship for a resistor is a nice linear one. It's Ohm's law, which is V equals I times R. I is current and R is the value of resistance, and V is the voltage across it. It's a very important one. You should all know it from GCSE or equivalent. There's an alternative form of Ohm's law, which is if we rearrange this to get I as a subject, we get I equals G times V. where G is defined as conductance, measured in Siemens, and you can see if you look at these two, it's just going to be 1 over R. So that's two ways of saying exactly the same thing. Sometimes this form is more convenient, particularly if we're dealing with currents. This form is the more common one because people tend to be used to dealing with voltages. But from a mathematical viewpoint, notice that R, the value of resistance, is just a constant of proportionality between V and I. So we've got, it's the equation of a straight line, but with no intercept. Yeah, y equals mx plus c. That's all it is, but simplified. Sorry about my creaking chair. Right, and in this circuit we have only two things. In fact, in all circuits, there's only two things we need to worry about. We just need to worry about V, and we need to worry about I. And V we would term the across variable. It's pushing, and I is the through variable. And that's the thing that's flowing, and it's linked by R. The relationship is linked by R. V equals I times R. And in every branch of physics or engineering, this is all you've got. You've only got two variables to worry about. You've got an across variable and you've got a through variable. You've got pressure and you've got flow. And you can see the analogy straight away with fluids. And so all these equations have their analogies in all different branches of physics and engineering. So once you learn one method, you can apply it to all kinds of other areas. And in fact, you can turn mechanical systems into circuit diagrams because a circuit diagram is just a representation of some equations. And that's actually quite an interesting thing to get into. Anyway, sign conventions. The voltage between node A and node B. So here's a node A, it's join of two elements. And this is another one, B, joining the same two elements but the other end. So this whole line here is a node. It's all at the same potential, and B is also a node. The voltage between node A and node B can be written VAB, which is the voltage of A with respect to B. So VAB, as defined across this resistor, is the voltage across this resistor measured at A with respect to B. Because remember, voltages are always differences. They are potential differences. Quite often they're measured with respect to 0. So you just say it's by volts or something. But normally you're measuring it with respect to something else, and it's a potential difference. So the voltage between node B and node A can be written VBA. So it's the same thing. It's just defined the other way around. So these will be the negatives of each other. VAB is equal to minus VBA. It's just a question of conventions and directions being defined. You can define a direction to be either direction as your positive. It doesn't matter as long as you're consistent. The answers will always come out the same if you're consistent. Current flowing from node A to node B can be written IAB. So the current is flowing from A to B, IAB. So the positive direction is A to B in this case. We could define it current flowing from B to A as being positive if we want to, in which case IAB equals minus IBA. Sometimes you don't know what the voltages or currents and things are, so you just have to guess which way is positive. And it doesn't matter because it's all in the definitions anyway. So the sign of an unknown voltage is positive when the direction of the voltage is such that the current flows from a high voltage to a low potential. So in this case, if we've defined the current as flowing this way, we would define VA as being positive. And then there's just the definitions of Ohm's law in the various things. These will all come out with the same answer if you keep your definitions correct. So the definition of unknown currents and voltages. Branch currents. So branch current is current flowing through a branch. Remember, the branch is a element with two wires attached to it. In the circuit below, the choice of direction of the current is arbitrary. It could flow either way. It could be going either way. We don't know because we don't know the values of VA and VB. Okay. If we assume that VA is bigger than VB, then the current will flow from VA this way to VB. This will be a positive voltage because you're going from a high voltage to a low voltage, and the current will be positive because it's going from high voltage to a low voltage. But if it turns out that VB is bigger than VA, then the directions of these, we can still use them, but in this case V1 will be negative because this point is higher than this one, so it's not a positive direction. And likewise, the value of the current will be negative because of the definitions. But we could equally well just turn these arrows around, and then it'll be positive in terms of our definitions. It's only about definitions. So you've just got to be very, very consistent with which way you define things. And there's not much more to say about that. Now, this is where it starts to get a little bit more abstract. We've got mesh current. A mesh current is the current that flows all the way around the perimeter of a mesh. So first of all, we have to know what a mesh is. And so we think back and we say, okay, this is a mesh. It's a sort of a loop in a circuit. So there's a loop here. There's a loop here. There's actually a third loop here as well, one that just goes all the way around like this. But we don't need to define that one. That's just being overkill. So in this one, we would just say, we'll go for the obvious. There's two loops here. We've got a loop here, and they've got a loop here. And we define this as a mesh, and we define this circulating current here. It's just a definition as the mesh current. So that's the definition of our mesh current. This is the definition of the mesh current in here as well. Now notice that this might not be the same as the branch current. This is the branch current. This is the current in this branch. This bit here is just the branch. This is the current flowing in that branch. Now here, Ix is obviously equal to I1. So the branch current equals the mesh current. Likewise here, we've got Iy being defined as going this way, and that's equal to minus I2 in terms of definitions. Now I3, the one through here, is a combination of this mesh current and this mesh current. And this one is defined as going in this direction, and this one is defined as going in that direction. So I3 is going to be Ix, which is in the same direction, minus Iy. So Ix is a sort of an abstract concept. You've got to be very careful where you measure it. You could measure it here because it happens to be the same as I1. If you measured it here, you'd have to also measure these other ones as well to get to it. So we're starting to get a bit abstract, where we're saying that this is a current flowing in this loop, but it's interacting with the current flowing in this loop as well. So just bear that in mind as we go forward. So this leads us on to a couple of very important laws, which in many ways is the law of stating the obvious. But it does require you to have a bit of understanding what currents and voltages are before we can say it's obvious. So we don't say it's obvious, we give it a name of Kirchhoff's voltage law, discovered by Mr. Kirchhoff in about 1880, I think it was. And his voltage law says, Kirchhoff's voltage law states that the algebraic sum of voltage drops around any loop in a circuit is zero. Right, so we add all the voltage up around this loop, and they'll all come to zero, and that's all we really need to know about it. But there are procedures, because we can get this very wrong if we get our definitions wrong. So we assign the unknown currents and voltages according to the sign convention, i.e. current flowing from a high to a low potential. So we assume that this is a positive voltage, we define the current going this way, and therefore these voltages will be defined in this direction as positive. And then we can say that V1 plus V2, so we're going, start from here, so we've got up V2, up V1, so that's V2 plus V1, must equal, effectively, VB, driving it around. So VB, the driving voltage, is equal to V1 plus V2, and then it's back to zero again, around the loop. So this is the formal way of doing that. So if you drew an arrow on VB like this, you can then, as you go around the loop, and in fact, I might try and draw an arrow. Let's see if I can draw an arrow. Pen. Look at that, there's an arrow. So now, having defined that as a positive voltage, you can see that what we've actually got, if we add these things around the loop, is we've got VB minus V1 minus V2, because we're going against the arrows. We're going with the arrow in this one. All the way around, you could say V2 plus V1 minus VB equals 0, and just add up to the same thing. Okay, so it's a straightforward enough idea. Oh, hang on, question. Won't the math still work out if we assign the arrows randomly? Yes, all you've got to do is being consistent with your definitions for every element. But it's best to stick with a convention because it gets messy really, really quickly. Right, so circuit theory. So this slide's in the wrong order. It's supposed to be earlier so that I can put breaks between the sections, but never mind. Right, so we've done Kirchhoff's voltage law. Kirchhoff's current law states that the algebraic sum of currents leaving any node is 0, right? Which is a bit more abstract in some ways. But basically what we're really saying is what goes in must come out. So here's a node in the circuit. So there's a nice node there. We've got currents, and you can start to see it's obvious because you can't have lots of currents going into a node with nothing coming out, because the node will fill up with electrons, and that's probably not a good thing. So we assign unknown currents and voltages according to sign conventions, or whatever convention you want. In this case, we've defined I1 as going in, and we've defined I2 and I3 as coming out. And so in this situation, we can say that I2 plus I3 must equal I1. What goes in must come out. And there really isn't a lot more to say about it than that. Definitions, you just got to get definitions right. If you made all these go into the node, that's fine. You could then say, I1 plus I2 plus I3 equals 0, but at least one of those currents would actually have a negative value in terms of the definition. Right, the answers you get may be negative if you use the opposite arrows. Well, you've just got to be good with your definitions. What I suggest you do is try these things out with examples, stick to your own definitions, and test it in the simulator, and then you'll get the idea of how these things work. Right, a voltage divider. Really, really useful circuit. You've probably come across them before. It's a voltage source in series with 2 or more resistors, and that makes a voltage divider. The voltage across each resistor divides in proportion to its value. So voltage source, 2 resistors, and we're asking ourselves, what's the voltage at this point here? So we can sort of tap off a voltage. And it divides in the ratio of R2 over the total resistance, which is R1 plus R2, and then we multiply it, and we mustn't forget to multiply it by V0 to give us our scaling factor. So it's a ratio multiplied by a scaling factor, and that gives us a fraction of the output voltage. Okay, we're actually applying circuit theory to get this answer, but it's so easy, it's not worth getting into it. But if you want to prove this kind of thing, we can say that I, the current through here, which is the same through both resistors, is equal to Ohm's law, V0 over R1 plus R2. So R1 plus R2 is the total resistance in this circuit. So the current going through it must be equal to V0 over the total resistance, R1 plus R2. V2 on its own is just IR2. We now know what I is. So we can make the substitution for I into here to get V2 is equal to R2 over R1 plus R2. So it's not rocket science. And really, electronics doesn't get any harder than that if you can break the complicated problems down into very simple problems. So if it's all as easy as that, that's great. And in practice, it actually is, but you've just got to be able to spot these little tricks going forward. So then the current divider. We've got a voltage divider. Can we do a current divider? Current divider, current source in parallel with 2 resistors. So this is a symbol for a current source. It's 2 circles on top of each other. You will see other types of symbol for a current source. Sometimes they're just circles like a voltage source, but with an I written against it. So just be careful about trying to spot what sort of source you've got. It's quite important. Right, so the current through each resistor divides in proportion to its value. So here are the 2 resistors. We've got a current flowing through here, and it splits into 2 paths here, depending on the value of the resistances here. And in this case, I1, it's a very similar formula to the one we saw on the other slide. I1, current through this resistor, through R1, is equal to R2, which is the other resistor, divided by R1 plus R2, which is the sort of total resistance, and then multiply that again by I0, which is great, except that's not quite as useful as it could be, because if you want to know the value in this resistor here, and you've got lots of other resistors in parallel up here, you need to know what all these other resistors are, so you can work out what this one is. Whereas all the currents in there, and it just gets a little bit tricky. So what you can do is couch it in terms of conductances rather than voltages. So we do exactly the same kind of thing to get a proof from this. So from Kirchhoff's current law, what goes in must come out, we can say, because of our definitions, so it's important to understand your definitions, minus I0 plus I1 plus I2 equals 0. Therefore, I0 equals I1 plus I2. It's just that rearranged. And then we substitute Ohm's law in for these two currents here, and we get I0 equals V over R1 plus V over R2. And sort of an alternative way of writing this, sometimes it's because you're lazy and you don't want to write scores or whatever, you can actually say that then I0 equals V G1 plus G2, where G1 is 1 over R1 and G2 is 1 over R2. So this is the conductance rather than the resistance. So it's exactly the same, it's just defining it slightly differently. So I0 equals VG1 plus V2. And therefore, V, we rearrange that, gives us I0 over G1 plus G2, which if you did it with resistances, you would end up with R1, R2 over R1 plus R2, which is a little bit more complicated than just 1 over G1 plus G2. Okay, it's the same, it's just a bit less complicated, because G1 plus G2 equals 1 over R1 plus 1 over R2, which is equal to that. So you can then just run it through a little bit more of the same kind of analysis, and you end up that I1 is equal to I0 G1 over G1 plus G2, which is the same if you simplify it as R2 over R1 plus R2. But in this case, we've got an R2 on the top here, or something relating to current 2. But on the top here, we've got something relating to current 1. And this just seems neater to me, that the current you're interested in is related in the equation to the element that relates to it. Whereas in this equation, it doesn't. So as a point there, so when dealing with currents, the G form may be more helpful, maybe slightly simpler. It gives you the same answer. It just looks neater to me. Up to you. So there's a bit of a comparison between the two there then. If you've got a voltage divider, it looks like this. You've got a voltage source, resistor, and a resistor. And if you want to know V2, it's R2 over R1 plus R2. So again, we were interested in V2, and we've got a component R2 in our equation. So they're sort of directly linked physically. And in the current system, you've got a current going through here splitting between two resistors. We've got I2, for example, is equal to G2 over G1 plus G2 times I0. So it just aid memoir, the same subscript here and the same subscript here, they just relate to each other. And there's sort of an elegant similarity between both these things, and there's a duality between voltages and currents if you think about series and parallel as well. And the nice thing is that these are obviously related. We can convert these circuits into each other. We can turn this current circuit into a voltage-driven circuit if we want to do, and we can turn this voltage one into a current-driven circuit. And that's the nature of circuit theory in the maths. This circuit is only representing an equation. If we have other equations, we can put this into a different form, and we can maybe write it differently. But we'll look at that going forward. But linearity is an important point that we have to understand. And the mathematical definition of linearity is that a function is linear if the sum of two excitations is equal to the sum of the responses of each excitation taken separately. So that's a lot of words, difficult to get a grip on what it really means. But mathematically, it expresses itself as if you have a function and you put a variable x1 into it, and you have the same function and you put variable x2 into it, if you then added x1 and x2 and put them in the same function, you'd get exactly the same answer. Yeah, x1 function x2 equals function x1 plus x2. And the interesting thing there is if you've got a complicated circuit with lots of sources, say x1 is a source and x2 is a source, maybe x3 and x4, what you can actually do is divide it into little problems. And you can just say, well, let's only worry about source 1, and that's this one. And that's easy to work out. And then we'll make that one 0, and we'll worry about source x2 and work out what the answer is there. And we just add the two together, and that gives us the total complex function. Right. Now, unfortunately, linearity is an important concept. Things that are linear only have resistors, inductors, and capacitors. Other things like diodes and other stuff are not normally linear. diodes are exponential, and there's no way that you can call an exponential linear. So we have to be a bit careful. But engineers spend an awful lot of their time trying to turn non-linear circuits with diodes and things into linear ones, so they can apply just this theory, basically all the network theory we're going to learn. Because if you can't apply the network theory to a problem, then the problem becomes quite hard to solve. So we will try and massage circuits to be linear. And it may be that they're only linear over small ranges of operations, so we have to constrain them. But we'll spend, or engineers spend a lot of time trying to make things linear, because it makes your life much, much easier. So understand what linearity is, because it really makes life easy going forward. Right, an ideal voltage source. So we're still on our sort of definitions now. I said it was boring, this first one. Right, so a voltage source. This is our voltage source. It's just like a battery or something like that. And an ideal voltage source, so the key is ideal here, is a voltage source which gives a constant voltage between its terminals regardless of the size or direction of the current through it. So the voltage here, let's call it 5 volts. It's going to drive a current through here through a circuit, which is represented by a resistor. So its circuit symbol for this bit here, not the resistor, just this source, is this, which is the battery symbol. So what we're really saying here is they're going to be whatever the battery voltage is, say 5 volts at this point, regardless of what we do here. And so if we put that into mathematical form or draw a graph of it, we can say whatever the current IS going through here, the voltage that comes out will be VS. So we end up with a straight line. Now we can see that this is ideal, because we just have to think what happens if we connected the output of this battery to itself without the resistor. In other words, a short circuit. The current in principle will be infinite because there's no resistance. So we apply Ohm's law there, we've got an R of 0. And so an infinite current is over, off the screen somewhere. And that's just not possible. So there are some limitations with the concept of an ideal voltage source. These things always fall down at the extremes. But they're very useful, because at 99% of all cases, the ideal voltage source is absolutely fine. But just remember that it's not. So a practical voltage source, so one that exists in the real world, is very easy to model. They're not capable of supplying a constant voltage independent of current, because you can short circuit a battery and you don't get infinite current, because that gives you infinite power. So it's just not possible. So there's something else we've got to include if we're going to go to such extremes. So in practice, the voltage reduces when a large current is drawn from the system. So we can model this by having our ideal voltage source and just putting a little resistor in series with it. And in an ideal world, for an ideal case, this value of this resistor would be 0. But in the real world, the value of this resistance will be small, a few ohms perhaps for a good battery. And this is what effectively these batteries losing their voltage as time goes on. This is called the internal impedance of a battery. And as a battery goes flat, it doesn't really go flat. What happens is this resistance gets bigger inside the battery, because the battery just has trouble getting the charge to run out of itself. So as you pull current out, you put your load, your light bulb or whatever on the output of this source here, because the internal resistance is now significant. As soon as any current flows through the battery and into your light bulb or whatever, you've got a potential divider, and this voltage here will drop. And the more current you take out, the more this voltage will drop. And a useful case to understand is that when this resistance is equal to this internal resistance, the current flowing through here, well, the voltage that you get across these 2 points will be half the open circuit voltage. And that's a really interesting point, but we'll look at that going forward. So effectively what we've now got is Ohm's law applying here, and we've got the equation of a straight line defining our voltage source. You can do a KVL around the loop and see what's going on. You've got minus VS, IS, RS, and then whatever the voltage P is across here. And so you can work out what the VP, the output voltage is. It's going to be VS, the voltage of your source, which remember is ideal, never changes, minus RS times IS. And that's the you end up with a slope. And now if you go to a short circuit condition, you find the voltage will be 0, which is eminently sensible. And the slope is actually the value of the resistance of the source. So we've gone from an ideal case to a practical case. We've applied a little bit of circuit theory to it, and we've got a working model for all kinds of voltage sources and an understanding maybe of what the value of this resistance means in the real world. So we're starting to get this abstraction and linking it with practical world. We can do exactly the same for a current source, an independent current source. People seem to have an idea about voltage sources. People understand batteries. People have less idea about current sources because they don't, battery isn't particularly a constant current source. But they're really, really useful things. So it's worth just getting it. And it's the same. It's just different definitions, really. So an ideal independent current source provides a constant current regardless of the voltage across it. So here's a current source. This is going to provide us with whatever this, say it's a 1 amp source. It's going to give us 1 amp under any condition because it's ideal. Yeah, ideal means it doesn't exist, right? So it's going to be trying to give us 1 amp under all conditions, whatever the voltage is here. So if we say now that whatever the output voltage is, or we make it to be, the current is going to be constant, we end up with a straight line here, same as before. And again, if you go to extremes, the extremes for the current source is when it's open circuit, as drawn here. Intuitively, you would say, well, there's no loop around here. There can't be any current flowing. And yet the current source is an ideal current source and therefore is forcing 1 amp to flow. It doesn't care what the rest of this circuit is. It's saying, I'm giving you 1 amp and I will do whatever is necessary to give you 1 amp, which is where this voltage can alter. This current source effectively alters its voltage to maintain this 1 amp. Now, in an extreme case, when it's an open circuit, it's really got to make this voltage huge so that the current can jump the gap. BS can be negative. Yes, it can. As I say, all this is going to do is maintain the current. So you could make this whatever you like, and this will just maintain 1 amp irrespective. It's a constant, and mathematically that's what it is. It's a constant. Now, obviously, in an open circuit, this is a completely impractical type of situation because you're not going to get infinite voltage and jumping in this gap, except in some certain extremes cases. So we have to look at what happens with a practical system. Taking that into account, and unsurprisingly, probably by now, there's a resistor involved, and in the case of a current source, it's a parallel resistor. So what happens now is if you don't connect anything to this point here, current can still flow through this internal impedance of the current source, and it depends on the value of this resistance as to what current that will be, and that controls the output voltage. So in the ideal case, the value of the resistor is infinite. So this will be an infinite value, and we'd end up with the ideal case. In a practical source, it's actually a big resistance because you don't want lots of current going down here. And again, if you do the maths in the loop, you end up with the equation of a straight line where the slope is defined as minus 1 over Rs in this case. So the important thing to remember is that the practical source has an impedance in parallel, and the practical voltage source has an impedance in series equivalent resistance, receive parallel resistance. Which leads us nicely onto this theory of superposition. So superposition. The theorem, and I shall leave this with you, we'll stop in a minute. The superposition theorem states that the response of a linear network with several sources is equal to the algebraic sum of the responses produced by each source acting alone, all others being suppressed. And this is very similar to the definition I just gave you for linear networks. Okay, so linearity at the bottom here. What I said was, if we take the sum of the individual sources and add them together, it gives us the overall response of the system, as long as it's linear. So that's what we can do. We have to suppress all the voltage sources and the current sources, only leave one operating, and then we unsuppress that one and go forward. And the easiest thing to do is to look at an example of that. Right, the really important thing to remember, and this is the thing that catches people out all the way through, that voltage sources are suppressed by replacing them with a short circuit. We set them to 0 if we replace them with their equivalent series resistance, which, remember, for an ideal voltage circuit is 0. Current source is the opposite. We replace the current source with an open circuit. And let's see what happens when we do that. As an example, derive expressions for I1 and I2. So here we've got a slightly more complicated circuit than we had before. We've got a voltage source, we've got a current source, we've got a resistor and another resistor. So the fact that we've got a voltage source and a current source makes this a little bit more complicated from things we've seen at the moment. So we would probably go to superposition and look at the effect of just the voltage source on its own. So we suppress the current source, redraw the circuit, and then we can suppress the voltage source, unsuppress the current source, redraw the circuit, work out what's going on, and then add those two solutions together. So if we do that, here's the circuit as it stands with everything active. We suppress the current source. Here's the current source. We're going to suppress that and we replace it with its equivalent impedance, which in an ideal world is an open circuit. So we just take it out, and we end up having taken it out with this. So this is this circuit with the current source suppressed. And you can see now that this is a voltage divider. So we can work out what the currents are. I1A is going to equal I2A because there's nowhere else for the current to go. And we can just apply the voltage divider rule to it to get that I1A equals I2A equals V0 over R1 plus R2. So that's our first solution. Very easy. We then suppress the voltage source. So here's the voltage source and our original circuit. We're going to leave this one in circuit. We're going to suppress this, and we suppress this. We replace it with a ideal impedance, which in this case is 0. So we've got a short circuit across here now. So if we draw that with it suppressed, you've got a current going through this resistor. You've got a current going through this resistor. So what you've got is a current divider. So now we can work out what the current is in this loop by applying the current divider equation. And again, you can either have the G version or the R version. Just remember to swap the subscripts. And that gives us the definitions of what the currents are in those circuits. And then we can just add those two responses together. So this is the response with the current source suppressed. This is the response with the voltage source suppressed. In this case, I1A equals I2A equals 0. I1B and I2B are equal to whatever we define them as being. And then to get the overall currents in the complicated circuit, we just add the individual currents together. And so we end up with slightly more complicated equations than we got, but the actual steps to get there were really, really easy once we've identified that we can do this linearity, and we've identified it's linear, and we can apply this superposition theorem. So that's superposition in a nutshell. And I think at that point, you've probably had enough, and I've certainly had enough, and we will pick this up at the next lecture. So I hope you've enjoyed that, and that's the end of today's show. See you later.